The Effect of Chitin and Acrylate on the Cleansing of Water Polluted by Artificial Dyes by Ben Glauner. Water pollution in the textile industry is a large problem across G20 countries such as Turkey, China, and Indonesia, and these three countries account for about 60% of worldwide emissions. This is significant because these are less affluent countries where the government cannot necessarily afford to use large, expensive systems to purify the water. Turkey, China, and Indonesia account for about 60% of water pollution from the textile industry. Their GDP per capita ranges from $12,000 to $26,000 in Turkey, China, and Indonesia, and the GDP per capita of a nation is how much each person makes in a year in that nation. This is concerning because the government cannot always afford to use large, expensive systems to purify the water, especially in rural areas where this problem is most rampant. Coagulation and flocculation is a chemical process that is commonly used in water purification because it allows for suspended impurities in water to be filtered out to precipitate out of solution and to be filtered out through classic methods. Once a coagulant is added to a solution, the coagulant, such as potassium alum, which is the most commonly used reagent, binds to negatively charged particles, which are suspended particles in water, and they form larger flocks and they can precipitate out of solution. Once they precipitate out of solution, they can then settle on the bottom of the tank, or it can be filtered out by a filter, and the water can then be chlorinated and sent into the water supply. Figure 4 shows an example of what an industrial spreadsheet for the process of coagulation on an industrial scale looks like. You have flocculation tanks and a settling tank. In the flocculation tanks, reagents are added and stirred at certain temperatures and certain speeds to try to get all the mixture to mix and bind and precipitate. This water is then sent into a filter to filter out any precipitates that are left in the water, and is sent into chlorinization to kill any bacteria that may still exist inside the water. Coagulation works as follows. Commonly, there are negatively charged particles that are suspended in solution. These cannot settle out because they are negatively charged, and negatively charged particles repel each other. This causes them not to settle out of solution, and this causes them to stay suspended. When a positively charged reagent or coagulant is added, such as potassium alum, this forms surfaces that are potentially positively charged. These positive charged surfaces allow for negative charged particles to fit in between and form larger flocks because negative and positively charged ions can bond with each other. This bonding causes larger flocks to form, which can then be layered onto each other and can form more and more layers. Eventually, the act of gravity will begin to exert, and these will be then allowed to precipitate out of solution. Removal of direct dyes by coagulation, the performance of preformed polymeric aluminum species by Shi et al. Shi et al. In this study tested the efficiency of 3 different types of aluminum, which were AiCl3, PaCl, and Al13, in the removal of direct black 19, direct red 28, and direct blue A6, and all 3 of these dyes were purchased from Sigma Aldrich. They tested the concentrations of aluminum at 0, 2, 3, 4, 5, 6, and 8 moles of concentrations, and they showed that from about 6 to 8 moles there was a little increase in removal of the dye for all 3 of them, and from 2 to 6 there was a steep increase in the removal from about 15 to a little above 80% removal. And so it's significant because it showed that that the most efficient concentration was about 5 to 6 moles of aluminum added to solution. Colloid interaction and coagulation of dye wastewater with extra application of magnetites by Liu et al. Liu et al. In the study showed that when ferric chloride, which is a magnetic powder, was added to dye, the settling time for the precipitation of the dye out of the solution decreased from about 21 minutes to 7.5 minutes. This was significant because the time for this reaction to take went down by about a third. The efficiency of the process did not decrease because the amount that precipitated out was stagnant, but the time that it took decreased significantly, which could increase the cost efficiency of this because more wastewater or dye-infected water could be put through the system and more could be sent out of the water, and the water could be cleaned at a quicker rate. Coagulation and flocculation of dye-containing solutions using a bipolymer chitosan by Gibel and Razzi. Gibel and Razzi showed that the molecular weight of chitosan from low and high molecular weight did change the way the reaction worked, but did not increase the lowest efficient point of such studies. As can be seen from these charts, whether or not it's a low or high molecular weight, the most efficient points were very similar to each other, in that they both removed about the same amount of dye in the 25 and 50 and 100 milligram concentrations, and that they did and that the same amount of chitosan was needed to get to the most efficient point. The purpose of the experiment is to test whether acrylate or chitosan are possible substitutes or supplements for the use of potassium alum. Both of these are a type of polymers, with chitosan being a bipolymer and acrylate being an artificial polymer. The null hypothesis is chitosan or acrylate exhibit no quantifiable benefit over potassium alum, and the alternate is chitosan or acrylate exhibit a quantifiable benefit over potassium alum. Black 19 dye will be created using 2 milliliters of distilled water for every milliliter of dye. Acrylate and chitin solutions will be created at 0.4 and 1.2 solutions, and these will serve as the experimental variable, and a potassium alum solution at 0.4 and 1.2 solutions will also be created, and this will serve as the control group. 3 milliliters of each solution will be added to a dye solution, and a preliminary pH measurement will be taken. The solutions will then be stirred for 5 minutes at 100 rotations per minute, and the solutions will be left to sit for 24 hours at 25 rotations per minute. After 24 hours, the final measurement of the pH will be taken. The solutions will then be fed into the spectrophotometer, and the wavelength absorbance will be recorded. It will then be compared to the Beer's law plot. The Beer's law plot will be created of the Black 19 dye. The max wavelength of the Black 19 dye will be recorded, and the spectrophotometer will be used to find the absorbance and multiple concentrations of Black 19 dye. These will then be plotted in Excel, and the line of best fit will be recorded. The final experimental solutions absorbance will be compared to the Beer's law plot to find the final concentration of dye, and this will be compared to the beginning concentration of dye. The data will then be analyzed using a one-way ANOVA test with IBM SPSS version 24. This is my budget. Items that are needed will be chitosan, acrylate, potassium alum, and reactive black 5, and items already owned are glass beakers at 250 and 1000 milliliters concentrations, a spectrophotometer, and curvettes for the spectrophotometer. And this is my bibliography. Thank you.